This video goes through the sequential entropy pooling theory and examples. This is something that I'm very excited about, and I think this will be one of the most interesting videos showing you the full depth of what entropy pooling can actually do. So first of all, we start by asking what is entropy pooling, and basically it's a views and stress testing method for fully general distributions. So it can either be historical observations or even better some Monte Carlo simulations that you have performed using either the fully flexible resampling method or some generative machine learning or even normal distribution or log normal distribution simulation if you want. But of course we want to have something which is as realistic as possible. So it's the framework that we work with in the portfolio construction risk management book, where at some horizon we have this matrix R, which contains joint scenarios for the P&L, returns and risk factors that we are interested in. So you can imagine here that along the columns of this matrix, this is where you have your Google, Facebook, Apple, and your risk factors such as implied volatilities and interest rates and things like this. Then for each row in this matrix, this is a joint realization for all these assets and risk factors. And for these joint realizations, we can assign joint scenario probabilities that we collect into a vector called P. If we then want to perform some views or stress testing, well, then we do it by changing these scenario probabilities into the vector that we call Q. And basically it has many nice features because once we have priced everything here in the prior simulation, then we don't need to do any repricing. And it's also very nice if we have derivative instruments and things like this, because entropy pooling is essentially just an equivalent probability measure change. And we have learned from derivatives pricing that if we have the price correctly on the one risk measure, well, then it's correct under all other equivalent probability risk measures. So this is a very nice nuance of entropy pooling, where we implement predictive views and stress testing when we use it in this way. This is what makes it incredibly powerful, besides being able to work on fully general distributions. So basically, entropy pooling, mathematically, it's the minimization of the relative entropy or the KL divergence. So this is the formulation that we have here. And actually, if you have uniform probabilities for this prior vector, then you can show by some rewriting that it corresponds to entropy maximization. So the theory for maximum entropy and relative entropy minimization and this KL divergence, it's actually quite well known and quite well established. So it's interesting that people in finance economics still see this as a new thing, because it's not. Okay. But just to give you just some intuition about what entropy pooling is, so you can imagine that we have this simulation, and for example we have simulated some developed market equities, and here we have the prior simulation called P. So this is just a log normal simulation, just to give us something to work with. Then we implement different views on the volatilities, means, and here also skewness and kurtosis, introduce more mass into the left tails of the distribution. So the elegant feature of entropy pooling is then that it gives us a predictive view here in this case. So if you look at this distribution here, it's the same as we have here on the left side, but just with some fill and a bit not as tall. Then we can see what do we expect to happen to corporate high yield, for example. So if we introduce more tail risk into equities, well, then entropy pooling will tell us that if you are to respect this prior simulation, then you would also expect more tail risk for corporate high yield. Of course, we could implement some views for corporate high yield if we didn't want this feature, but usually when we perform views and stress testing, we want help with determining what happens to a potentially very high dimensional simulation when we adjust one thing that we have a view on. All right, so then there's this question that why do we use this relative entropy in KL divergence? And basically there's this article which shows that when we perform an updating in this way, it has some very nice properties, and that is a generalization of Bayesian updating. So it's a generalization in the sense that for Bayesian updating, usually you have a prior model before you see the data, and then you see some data, and then you get the posterior. With this generalization, we have a prior model which can be based on some historical observations or whatever we want, and then we have some views or stress test for the posterior that we want to have. Then entropy pooling helps us to get this update in a very, very good way. So this is shown in this article. And there are also some people who wants to have an interpretation of this, entropy quantity, like what does this value actually mean? And there are many different applications where entropy has some interpretation, but in this case for our posterior updating, then the authors actually make the arguments that it needs no interpretation. It's just has good properties, similar to mean squared error having good properties for linear regression, for example. So although the mathematics of entropy pooling can seem very, very abstract and not intuitive, actually when you work with it and the input you give the method and then the output that you get, it's actually very, very, very intuitive, the results that come out. So usually people they believe in this, but just going through all the mathematics, it's quite intense. So most people they skip this part, which I think it's okay. The important point is to know that somebody has done the work, somebody has proved the theorems and the results, so you don't have to reprove them again. All right. So the question is then, what are the main limitations of entropy pooling? And basically the way that the problem is formulated is as a minimization of a convex function, which is this relative entropy, subject to linear constraints on the posterior probabilities. And this makes it so that we can solve the problem in a very, very fast and stable way, even for very, very high dimensional simulations of a million scenarios if we want. But it of course imposes some limitations on the views that we can specify. So although we can specify views that are nonlinear functions, well, they still must be expressed as linear constraints of posterior probabilities. So it's an important separation. It can be nonlinear functions of the market, such as the variance, but it has to be expressed in a way that it's linear in the posterior probabilities. So what we can see here is that when we look at the variance, it becomes already nonlinear in the posterior probability. So this is a view that if you want to specify an equality or inequality in one of the two directions, this is how you would do. But then you can see that this term here, it's nonlinear, so we have to fix it to some value. So the original article, which was published in 2008, it just says, okay, just fix it to the prior value. But the point is that this usually introduces some implicit views which can be quite strong when we work with the method in general. So this is why we came up with a different method, which is called sequential entropy pooling. And basically, sequential entropy pooling tries to come up with better fixed value estimates than the original suggestion of always just using the prior when necessary. And usually when we work with this in this way, it gives us much better results. So much better results in the sense that the relative entropy is lower and we get some nice distributions that actually look like what we would expect in reality. So this is the theory that we just will be going through here, but of course it's documented very, very detailed in the portfolio construction risk management book, or even in the sequential entropy pooling article. So the essence of sequential entropy pooling is to take the different kinds of views that we have and then partition them in some specific classes, and then we just perform multiple entropy pooling updates, and we only fix values when absolutely necessary. So here for the first heuristic, we have, let's say we have views on the mean, volatility, skewness, kurtosis, and correlation. We can also have views on variances and CVAR, and I will talk about it a bit later. But the idea is then we say, okay, if we want to implement our mean views, then we can do that without fixing anything else. So we can perform the correct update here. So that's the first thing we do, and then we get a new posterior probability vector which we can use to compute new posterior values. So now we have updated our mean views, and we can use all the updated means to specify our variances views instead of just using the prior. Because let's say if I have a simulation for US and European equities, and I implement a view on European equities, for instance, that it should increase or decrease a lot, well, then we would expect that also something would happen to the expected return of US equities, for instance. And if I then have a variance view on US equities while I still use the prior, well, then in the original suggestion of how to use entropy pooling, I introduced an implicit view which can be quite strong in many cases. So that's the essence of what these algorithms try to avoid. So basically, once we have implemented the means, we update the volatilities, and then we can use these values to implement the skewness and kurtosis views, and then finally we can go to correlation views. If we have value at risk views, we can do it in the first processing. It requires us not to fix anything, while if we have CVAR views, we have to do it at the end after all of this. But I try to keep this slide nice and simple. So basically, we have two different ways of processing it sequentially. One where we always use the prior as the starting point when we have this relative entropy minimization, and then the other one is that where we use these intermediate posterior probabilities that we obtain. So this H2 is actually the algorithm that I came up with initially because I thought it made more intuitive sense. But then I discovered that actually if we do the optimization relative to the prior, always then we get better results. And it kind of makes sense because of course it's the relative entropy to the prior that we want to minimize eventually. So that's good that each step is performed in this way. Okay. This is something that you can look into and try to explore to see for yourself that these algorithms gives better results than the original heuristic of always using the prior values as fixed values. Okay. If you want some references for all this theory I just went through, then there's this first original article called Updating Probabilities, and then there's this article that introduces entropy pooling in 2008, and then with entropy pooling there is a related number called the effective number of scenarios. This is also something that we talk a lot about in the portfolio construction risk management book, and that we use in the fully flexible resampling method. So this is the original article, you can look into that. And then there's my article here that introduces the sequential entropy pooling heuristics, which you can study here. But actually in the portfolio construction risk management book, I give a much more coherent presentation of entropy pooling and all the nuances and all the views. So I think you can look into that if you want the full presentation and not just the sequential algorithms. Okay. So next we get to some examples, and here we have many Python case studies that we'll be going through. The first one, I will just present the results and then we can go into the code and look how we actually generate it. So here you can imagine that we have this multi-asset simulation where we use a log normal distribution. And this is the multi-asset data that follows with the fortitudo.tech Python package. So here we just specify how the prior simulation look. So we have the means, volatility, skewness, and kurtosis, and of course for the prior, then this effective number of scenarios, because it's uniform in the probabilities, it will be equal to 10,000. This is the number of scenarios we have, and the relative entropy with the prior with itself, it's of course 0 because it's the same probability vector. So then we go ahead and we implement some views on the expected return of private equity, the volatility of emerging market equity, the skewness and kurtosis of developed market equities, and then actually also the correlation of corporate investment grade and high yield. So then we have these two different algorithms. for the sequential processing. So the H1, it gives us an effective number of scenarios of 8,158. So this is how concentrated our probabilities are and the relative entropy of this value. So first of all, we verify that all our views are satisfied, and the view we implemented is that the expected return should be 11% for private equity, the emerging market volatility should be less than or equal to 25%, and that the skewness for developed market equities should be minus 0.75, and that the kurtosis should be more than 3.5. And then we have a correlation view also, which we will see in the code. But the point here is that we also have this H2 update and then the original one. So what we can see is that the H1 heuristic has a lower relative entropy and higher effective number of scenarios, while the original suggestion has a higher relative entropy. And here basically these green circles, they mark where we use this sequential updating to update the means and volatilities before we implement the views. So this is what you could see from the previous slides. For the original heuristic, we have to fix the means and the volatilities to update these things, because we just have to update everything at once. So when you look at the red circles and then the prior simulations, then you can see that it has the same values. So it has the same means, the same standard deviations, while for the sequential algorithms, when we lower the expected return of private equity, well, then we get a lower expected return also for emerging market equities and developed market equities. So we use that when we implement the volatility view for emerging market equities and the skewness and kurtosis views for emerging market equities. Also for corporate investment grade and high yield, we have updates of the means and volatilities before we implement the correlation view. Okay, so let's now go into the code and look how these computations have actually been performed. So these examples belong to the investment analysis module, and it's example 2 and 3 that we'll be going through today.